How's everyone doing? There being any new questions you would like to discuss, any specific topics? Let me bring my book just in case. Um, okay. Oh yeah, perfect. That's good. Let's start there then. Okay, so let's keep doing more integrals in that case. Let me see. There are actually some integrals which would be fine, useful to discuss. So yeah, I'll do. I think I have some ideas on which ones we could also do. Because they're kind of very classic integrals, which is good to have around. Okay, so but let me start first with the problem 5 from the review. And then I'll move to the other stuff. So let's see. Just trying to locate it. Oh, and then I also have some others here. Okay, there are a couple of things we can do. Oh, okay, it is the final. Yeah, I kind of put it in a weird location. Let me move it around. Okay, so problem 5. Oh, okay. Yes, this one about okay. So for this problem, let me see. Is my screen okay? Yeah. Okay. So most of the integration problems which are interesting require some sort of substitution. So first of all, the fact that this is like a definite integral tells you the way we're doing this is like first find the antiderivative for the indefinite integral. So let's find first this thing, and then we will put the bounds back in after we're done finding this. Okay. Now the thing is that this is like, if you prefer to write it in a different way, you can write it like this. Okay. So the thing is like, if you knew it, like if we only had, you know, if instead of like 1 plus y squared, we had like x to the negative 1/2 and no y, right? If this was only like x to the negative 1/2, then we could find this integral using the power rule for integrals. The problem is that it's not there. It's not yet in that form, but it's kind of again like the substitution is like the opposite of the chain rule. You kind of the idea is to realize that the derivative of this expression is more or less what you see outside of it, because the derivative of this is 2y, and here there's a y, so that's what suggests doing the substitution. So let's try to think about this one. So what if we do u equals 1 plus y squared? So you can say du dy equal, oh, sorry, du dy. It looks a little bit weird because I wrote the variable in terms of y, not x, but du dy is 2y. And so du equals 2y dy, or du over 2. Oh, okay. Let's check. I could have. You mean like that? It could be that I made a typo. So yeah, it could. Good. Let's check in a second. Yeah, no, it could that could have been. Good, good. So far so good. Is it making sense? Like the substitution, everything. Is that okay with everyone up to this point? So, yeah. So the purple stuff is what you see here, right? That becomes du over 2. And the stuff inside that's minus, which is to the minus 1/2, is u. So you get u to the negative 1/2. Okay. And then if you remember, the exponent rule or the power rule is to add 1 to the exponent and divide by that same number. So when you add 1 to the exponent, it becomes u to the 1/2. And you have to divide by the new number. But there's still like a 1/2 that comes from here. And that has to be added plus a constant, right? So it starts taking this shape. Here you have to be a little bit careful just because it can be a bit confusing because the 1/2 is in the denominator. What it ends up doing is moving that 2 upstairs. So you get 2 u to the 1/2 times 1/2 plus c. And so, oops, plus c. And so you end up, the 2's cancel and they're square root of, so you just get square root of u plus c, which is, what is u? U was like 1 plus y squared. Is that making sense? So what I'm saying is that the antiderivative or the of this thing is root of 1 plus y squared plus c. And again, the nice thing, that's how the good thing about these antiderivative problems is that if you're not sure, you can always take the derivative of this expression and check whether it gives you the inside or not. Right, so it does, if you remember how to take the derivative for this, it does give you the antiderivative. So is that okay? So sorry, it does give you this expression. So that's why this is like the correct antiderivative. So far so good. Are we okay up to this point? And then, yeah, I don't know, maybe I made a typo, the solutions when I wrote them down. So if you want to do that, was it the integral from 0 to root of 3 on the problem? Let me check. So yeah, if you want to do the integral from 0 to root of 3 of that, let's see. Where's the, no. Here it is. If you want to do the integral from 0 to root of 3 of that, it's just what we just found. Is what we would just found, evaluated. You have to evaluate this at the top value, which is y equals root of 3, and at the bottom, and subtract the answers. So when you put y equals root of 3, you get root of 1 plus 3 plus the constant. And then when you put y equals 0, you get root of 1 plus c. Right, so the constants cancel, so you get like root of 4 minus root of 1. Hopefully, I mean, I don't know if that's what I wrote, but that should be 1. That's answer. Is that making sense? Okay, yeah, so that was a mistake, yes. Then I may have forgotten, maybe I forgot to subtract this, I don't know. Or when I plugged in y equals 0, maybe I made a mistake. So yeah, so there should be a good, so there is a typo in the PDF solutions. Thanks. Okay. Oh, let's do, okay. Is that, yeah, I have some ideas of some that can be fun, just continuing with this substitution idea. So is that making sense? Everyone okay so far so good? Here's another example, which is a fun one. So let's say you wanted to find, uh, let me see how. Okay, yeah, let's say you wanted to find this. Like I'll give you a second to think about how you could find this. So try to think about what could the solution be in this case. Just give me one minute. So what's nice about this problem is that there's actually two different substitutions you could try. So it's nice to see that there's not always like a unique substitution you could go for. So what's a substitution you could try here? I mean, actually, there are a couple of ways we could do it, I think. Yeah, there are a few ways we can try. So what's one like this is a nice example actually. What's one substitution you could try? Any ideas? Uh, Close, very close. Okay, let's try to see what happens if you go with that one. It's close to one that we should try. Okay, so what is the u d theta? What's the derivative in this case? Uh, is actually the derivative of that's the problem. The derivative of tan is secant squared, but the derivative of secant squared is not a tan. It's like it's backwards actually. So the derivative of this is 2 secant of theta times the derivative with respect to theta of secant of theta because you have to use the chain rule, right? But it's not going to be 10 because what was the derivative of secant? It was secant times tangent, the derivative of secant. Um, so you end up with oh, okay. Actually, okay. This will work. Is this going to work? Yeah, no. This substitution does work, but for different reasons to the ones. It does work, but you just have to be careful with the derivative you're taking. So is it clear what the derivative is? Is it clear what the derivative is? What I wrote here. And that's a key step. Because again, this is kind of like something squared. So you have to take the chain rule. Like, the first thing is like the 2 comes down, you lower the exponent by 1, and then you multiply that by the derivative of secant. So this gives you 2 secant square of theta tangent of theta. Okay? So the u over 2 is secant square of theta tangent of theta d theta. So in fact, we can do this problem like in 4 different ways, which is nice. So I like this one. Is that okay? Is that making sense? That is actually right. That's another substitute. Yeah, there are a bunch of options. Like I like this one because we will have like 4 or 5 different ways to do it. But is that making sense? So all like what happens if you do this substitution? What happens if you do this substitution is that all it's maybe good to see that this can occur. All of this just becomes immediately du over 2. So the integral just becomes du over 2. And I mean, there's nothing else to substitute. All of it just gets into the form into the expression for du. So the question is, what's like again? What's it may be, it may take a little bit to remember this, but what is the derivative, like the integral of the u over 2? It's like finding a function whose derivative is like basically 1/2, right? So what is that function? It's the easiest example. It's the easiest antiderivative, right? So it can be the most confusing because of that. So if you plug this back in, what was u? U was secant squared over 2 plus c. And yeah, if you take the derivative of secant squared uh, of theta over 2, you will get, it's basically what we just did, right? If you take the derivative of this with respect to theta, you get 2, which cancels these 2. Secant of theta times the derivative of secant, which is secant times tangent. So you do get, so this does have the correct derivative. Is that making sense? So far, so good. Now, here's the second alternative. I'm just trying to say that it's not the only way to do it. So here's another possibility, option 2. I think, yeah. So yeah, the other possibility, which is what I would have go with if I was trying to do this problem on my own, would have been to just go with u equals tangent of theta. Like psychologically, that's the easiest thing for me to see there. So what happens if you do tangent of theta? You get du over d theta equals secant square of theta, right? And so du becomes secant square of theta d theta, right? Is that making sense? It's just because like the advantage of doing this substitution is that you kind of already know, but you have memorized the formula for that derivative, so you don't have to think about using the chain rule or anything of that sort to find it out. Okay, so what does that give you now? Uh, tangent becomes u, and this stuff becomes secant squared d theta becomes du. Is that making sense? So you just end up with u du, and that's like the integral of that is u squared over 2 plus c. Um, but what is u equals tangent of theta? So you get tangent square of theta over 2 plus c. Is that making sense? So far so good. And there's something that looks weird here, so I don't know if, but we should discuss it. So, um, So far, so good. Okay, so why would I say that this works? Because if you take the derivative of this with respect to theta, you should get this on the inside, and that does work. But does anyone notice something odd if you compare this answer versus the other one? Or do they seem completely, is this completely unproblematic? Here we're getting tangent square of theta over 2 plus c, and here we're getting secant square of theta over 2 plus c, right? So is that okay? I mean, what about that? Does that seem good or not? Well, so what could look a little bit confusing is that if you look at this, like these two functions seem very different, right? It's weird that they would be the same. And so that happens many times with trigonometric functions because there's a bunch of identities relating them. So I don't know if does anyone remember, like there was an identity that relates tangent with secant. Anyone remembers that one? Here's one way to remember it. You can start with this one, which equals what? What is sine squared plus cosine squared equals what? Uh, it equals 1. This I do expect everyone to remember. It is very important to remember this identity. It's kind of very useful. The others, like I mean, they're less important, but this one definitely should be one that everyone knows. So if you take this equation, if you divide both sides by cosine squared, what are we getting? We're getting sine squared of theta, cosine squared of theta plus 1. What is 1 over cosine squared? Well, 1 over cosine squared. Remember that secant is 1 over cosine, right? So 1 over cosine squared is actually secant square of theta. Is that making sense? And what is sine square over cosine square? That's just tangent square. So you end up with the identity tangent square of theta plus 1 equals secant square of theta. Is that okay? So what that really says is that tangent square and secant square are more or less essentially the same function except for a constant. And so that's another reason why. So if you want to do this, you can say that this is secant square of theta minus 1 over 2 plus c, right? And so you get secant square of theta over 2 plus c minus 1 half. So you see, you're getting secant square of theta over 2, which is the same that you had here, plus a constant. I mean, and this is like, that goes back to what we were saying, that you can always relabel the constants with different names if you want. Is that okay? So I'm just saying it may look different. So look like they may look completely different, but that's just because you're not using you were not using the identities that relate the different trigonometric functions. Once you use them, they are more or less essentially the same answer. Is that making sense? So it is just like it's a good example to see that you have to be careful sometimes with what the what the answers look like, because you might think that you got the wrong answer just because you didn't write it in a specific way, but it could just be that there are like identities that relate the different answers and things of that sort. Is that okay? Is that first? Okay, let me go to option 3. Here's option 3. And so as I said, there are tons of ways in which you could have solved this integral. I'm trying to show you all the ways I can think of, just for people to realize that sometimes there can be a lot more flexibility in these problems than you may think. So let me think about this in this way. Right, this is the same. I'm just breaking the secant square in a weird way, secant times secant. But I mean, that's fine. You are allowed to do that. But if I do it this way, that kind of suggests another change of variable substitution, which is what? Well, if I write it this way, is there like a suggestion of what could be the change of variables or the substitution? Uh, well, you should write u equals secant of theta, because what? The derivative of secant was secant times tangent. So if you write du d theta is secant of theta times tangent of theta. So now you can say that du equals secant of theta times tangent of theta d theta. And literally all of these, then the last few factors become du. So this integral becomes like the integral of secant, which is u, and the other one is du. Oh, good. And we know how to do this one. It's u squared over 2 plus c, but u is now secant, so you get secant squared of theta over 2 plus c, which we had found before, right? We had found this version before, but before when we found it, we had made u equals secant squared. So this is a good example where u equals secant would also have worked. Is that making sense? And here's a last option that I can think of. So here's another one. Option 4, which is good to know that you also can use from time to time, is that let's write everything in terms of sine and cosine. That's also a nice thing to do. So what is secant square in terms of cosine? As I had said before, is 1 over cosine square of theta. And what is tangent in terms of sine and cosine is sine of theta over cosine of theta d theta. Okay? And so I'm going to rewrite this as sine of theta over cosine cubed of theta d theta. And can anyone think about a substitution to make here? Uh, one that you could make is u equals cosine of theta, for example. If you make u equals cosine of theta, du d theta is minus sine of theta. So du is minus sine of theta d theta. So negative du equals sine of theta d theta. And so this integral becomes sine of theta, the theta is minus du. And cosine cubed becomes u cubed. So you're really integrating what? You're integrating minus u to the negative 3 du. And that's minus u to the negative 2 over negative 2 plus c. The negatives cancel, and so you can write it 1 over 2 u squared plus c. But what was u? It was cosine. So it's 1 over 2 cosine squared of theta plus c, which, since 1 over cosine is secant, you can write a secant square of theta over 2 plus c. And so you get back to the secant square over 2. Does that make sense? Is that okay? So it's a good example just because it shows you that even like a single integral can be solved in many different ways. So it's not like a reason to be concerned if you find different ways to solve the problem. There's some sort of like flexibility here, especially when it's trigonometric functions, because they just happen to have a lot more like identities relating them. So that it gives more flexibility for these problems. Is that making sense? So yeah, that's a good example to have. I don't know. Is there any other problems you would like me to go over? Yeah. Number 7. Let me check. Oh yeah, that one is that one is a good one. Yeah, I like this one. So the thing about this problem is that you want to find the derivative of the integral from 5x from x squared to 5x of cosine of t cubed dt. Okay. So let's see. The thing is like here, this is like a fundamental theorem of calculus problem. So the problem with this problem is that both of the bounds depend on x. Oops, sorry about that. Yeah. So both of the bounds depend on x in this problem, right? Usually, before maybe I should start with what the fundamental theorem of calculus said, right? The fundamental theorem of calculus says that the derivative and the integrals vanish, right? Like when they meet, when they see one another, they disintegrate, right? So the way in which I have written that, I mean, there are two ways in which you could write that typically, is that if you're taking the derivative with respect to x and the integral goes from a to x, these two kind of cancel. And the price for canceling them is just to get the function that you have inside, but in terms of x. The way in which I have been writing it more often is like when it's a derivative with respect to t. But again, it's kind of the same principle. When like the derivative sees the integral, right? when the derivatives is the integral, they go away, and you kind of are just left with the upper bound, which you insert into the function. Is that making sense? So that's kind of like the fundamental theorem works when these just like the upper bound just happens to be the variable itself. Okay. So that's like the fundamental theorem in a nutshell. The problem here is that we don't, these bounds are not just x, right? If they were just x, we could try to apply the fundamental theorem directly, but it is a little bit more complicated, right? So we're trying to find. So what we're trying to find is this derivative, right? Okay, so the first thing that you have to do is that you cannot have both bounds with the variable. So you kind of have to split the integral into two pieces so that each piece has like one of the variables. So how can you do that? There was a property of the integral, a splitting property of the integral that I had mentioned before, which is that you can break an integral into, at some point, right? I don't know if you remember this, but so here you can break the integral at some point, which can be any point. That's a cool thing. So you can say, for example, that this is like the same as the derivative from 0 to the derivative with respect to x. Okay. From x squared to what's a number that you like? Let's say x squared to 1 plus the integral from 1 to 5x of cosine of t cubed dt. Okay. Is that making sense? Maybe I should emphasize this with a different color. So you can break the integral with any like the lower bound continues to be the lower bound, the top bound continues to be the top bound. It's just that I have inserted kind of like a number like in the middle where I'm doing the breakdown. Is that okay? And it doesn't have to be 1. It could have been 0. It could have been -1. It could have been 3. It actually works fine with any number. As long as you put the same point in the breakdown. Why do we do that? Because now this has the advantage that on each of individual integrals, basically, I mean, if you want to recall, this property that I'm using is that the integral from a to b of f of x dx or f of t dt. I mean, just to write down the property I'm using is the integral from a to c of f of t dt plus the integral from c to b of f of t dt. So it's kind of like this breaking property that I'm using here. Okay. And then, yeah, the advantage of doing that is that now this one has only one variable on the top, and this one only has one variable, but this one still at the bottom, so we have to move it to the top. So the other property that you need to use for this problem is that you can change the order of the bounds, but the price to pay is like to put a minus in front. So the bounds can be flipped if there's if you just multiply by -1. Okay, so if let me continue with this problem. I'll just copy paste it to make it easier for myself. So if we keep continuing in this problem, what I'm going to do now is flip the first integral. Okay. Is that making sense? So the only thing that I did here was to flip. So maybe I should put this like with emphasis. So let me change the colors here to make clear that that's what I'm affecting now. Okay, so now we're getting close to what I want because each integral has like the variable at the top. It's just that it's still not just like the variable, it's like the variable in some weird expression, like x the variable squared or times 5 times the variable. So it's not quite yet in the format that we want. But before dealing with that, what you can do now is first break it into a sum of two derivatives. And then we can deal with each of these individually. Okay, so the way to do each of these individually is to do the chain rule. So here's we have to do the chain rule. We have to do two chain rule problems. So for so here now we're going to use the chain rule. So for the first one, we're going to call u equals x squared. So that way we end up with the derivative with respect to x of 1 to x squared, but 1 to x squared becomes u cosine of t cubed dt. And again, you're taking the derivative of that. You want to take it now with respect to u, so you make the usual trick. Right? So I multiply and divide by du. And we're almost okay. And now finally we are in a situation where the derivative and the integral kind of go away because there is just like the variable u on its own. So this goes away with this, so you get cosine of u cubed. And what is du dx? Du dx is 2x. But what was u? U equals x squared. So you get cosine of x to the 6th times 2x. Or 2x cosine of x to the 6th. That looks a little bit better. Is that making sense? So that's the first derivative. Is that okay? Okay. Then the other one is exactly the same, but what should be u in this case? U should just be 5x. And I apply the same logic. I use a chain rule. But again, no, this is fine. This disintegrate. So you just get cosine of u cubed. And what is du dx in this problem? It's 5 now. But what it was u? U is 5x here, so you get 5x cubed times 5. So you can write this as 5 cosine of 125 x cubed if you want. Okay. And after you have done that, now it's just about combining these two formulas, right? So the actual quantity that we were after was this, but we just have all the two pieces, right? The first derivative is multiplied by minus, so you get minus 2x cosine of x to the 6, and the other one is plus 5 cosine of 125 x cubed. Okay, so it's just like a interesting problem to check the fundamental theorem of calculus, and to check the chain rule, and to check the properties of the integrals. So it kind of has a lot of things in together. Is that making sense? Okay, good. Let's take a 5 minute break. Think about anything else that you would like to ask. If not, I can give you some more. We can do some more integral problems. But yeah, let's take a break. And in 5 minutes, yeah, if we find something else you want to ask me, just let me know and we can discuss. Let me do, okay, I think this can be fun to try. I don't know if I have done them, but these are two also useful integrals to have, to know. So here are two that you may have seen already if you're reading the book, but I don't know if you are. So how could you find the integral? Here's another example. How do you find the integral for tangent of x? Because we don't really know a function whose derivative is tangent on the top of our heads. So the idea for this problem is to use it. To use the fact that tangent is sine over cosine, and once you write it that way, what's the substitution you could use? You can do u equals cosine of x, for example. So if you use cosine u equals cosine of x, the u dx is minus sine of x dx. So sine of x dx becomes minus du. Okay. And then this becomes sine of x dx becomes minus du, and cosine of x becomes u. Okay, and so that gives you minus a logarithm minus ln of absolute value of u plus c. And that is minus ln. What is u is absolute value of cosine of x plus c. And that's the answer. It's more common. If you'll see it on the book, if you remember the rules for logarithm, you can move a number as an exponent back into the logarithm. So you can write this as cosine of x to the -1 plus c, and that gives you secant of x. Is that making sense? Is that okay? So the integral for tangent is natural log of secant, basically. Here's another one. Okay, this one, it is definitely more tricky. like this one is fine. It's like a substitution. The other one is like I don't even know who would have been the first person who came up with this, because it definitely is like it does require like I don't know. There's some luck to having the right insight, which is the integral for secant of x. Okay. So yeah, I mean, it kind of very weird. Like again, I'm not sure like how would anyone think about doing this, but I mean, I think it could. It's worth like just mentioning it because it does appear in the book. So so like the integral for secant of x, if you want to find it, the idea is to do a trick. Um, so what's the trick? The trick is to multiply and divide by secant plus tangent. Which again, how would anyone find this out? I have no idea. Okay, so let's do that. Uh, if you do that, then the top, the numerator becomes secant squared of x plus secant of x tangent of x, and the denominator is still secant of x plus tangent of x. And then if you do that, then there's like a substitution you can make, which is what? What could be a substitution which is useful to make in this problem? You can make u the denominator, which is tangent plus secant or secant plus tangent. And if you do that, then you get du dx is secant square of x plus secant of x times tangent of x. Okay, which is precisely the numerator. So it's kind of miraculous. I mean, this one is a bit miraculous. So you end up with du over u. Is that making sense? And now it's a usual thing. It's like ln of u plus c, and this is ln of secant of tangent of. I mean, usually that's how it's written. So that's what that one would give you. I guess I'm not expecting you to. I mean, like for a problem like this, I would definitely give like a hint of what to do because it's not like so clear how to come up with the substitute, like with what you would need to do here, which is like to multiply and divide. So that one is a little bit more tricky. Let's see. So far so good. Any questions about this? Okay, now let's do this one, which is also interesting. Uh, So this one is a fun one. So let's try to think about what to do for a problem like this. So what would you say in this case? What could you try? Uh, it depends. I mean, I guess it depends on what you mean by factor out. You mean like rewriting sine cube as yeah, it depends. You may be saying the correct thing. I'm not sure like how to just interpret the factor out part. So you're saying like something like maybe is this what you are saying? Something like that? Okay, okay, okay. So it's still all under multiplication, right? So if you write it, I mean, you're getting close, but okay, let's go with this. So if you write it that way, what would you do next? I mean, it is close to what we need to do. It's not so clear to me just if you, in this particular version, um, because what could you do now? Mm, yeah, it's not so obvious what to do here, unless you had a specific idea. Although it is true that you have to factor something out, but it's not quite the way you were doing it. It's slightly different. What it does make sense is to break this sine cube as sine times sine squared. And the reason for that is that you can now make, for example, what if you make u equals cosine of theta? So du d theta is minus sine of theta d theta, right? So this gets taken care of with the with the sorry, so du. So this takes is gets taken care of with the du part because it just becomes minus du, the thing in purple. Uh, the other one, this is going to become u squared, right? So the only thing that's left is what would you do with sine squared, right? What's the possibility? How can you get rid of the sine squared part? Or how can you replace the sine squared? Is there something that relates sines with cosine, like an identity? This is where you have to use the identity that sine square is 1 minus cosine square. It's the same that I wrote a couple of pages ago. Right? So if you do that, then this is 1 minus u squared. And now you do have everything in place to replace. So sine of theta d theta becomes minus du. Sine squared becomes 1 minus u squared. Cosine squared becomes u squared. Okay, so this becomes minus 1 minus u squared times u squared du. And this is my, how do you integrate this? Like the best thing to do is multiply this first. So you get u squared minus u to the 4 du. In fact, you can put the minus inside to write it as u squared minus, sorry, as u to the 4 minus u squared du. And this is easy. This is u to the 5 over 5 minus u cubed over 3 plus c. But u was cosine of theta, right? So you get cosine to the 5 of theta over 5 minus cosine cubed of theta over 3 plus a constant. Is that okay? No, I don't think I had anything that used something like that, but it's like a good thing to know. There is like, is that I kind of yeah, running out of problems to do. So like I thought, okay, this could be interesting. But yeah, it is I actually think wait, let me check. This could be um let me check the book topics. Um, where could this be? Okay, okay. Yeah, this is a preview. Okay, now I remember. This type of this one that I just did, this one that I just did, it is more common in Calc 2. So yeah, I wouldn't ask this one, but I thought, but it is like you know, it's kind of like a maximum of difficulty or above maximum difficulty, but it is kind of it's a good reminder of the identities, and things like that. Yeah, like the problems with substitution that I have in mind are a lot more like straightforward. So like this one, yeah, like this one is yeah, I wouldn't ask something like this unless I gave you like the identity, like but still I wouldn't do it. For this one, again, I still probably I don't think it makes a lot of sense to ask for something like this because no one will ever think about doing this unless you're told. But this one is yeah, this one is more reasonable. This one is fine. Definitely these ones are fine. Yeah, all the others are fine, but the last two, maybe more like to discuss them more than anything else. Yeah, is that it? But if you end up taking Calc 2, then you'll definitely work with a lot of those that look like this. So it's kind of like a preview for that. Um, are there any other problems anyone would like to go over? Let's see. Okay, so we still have all of tomorrow, because we still can do more problems if you like. So, okay, I can, yeah, so think about like go over again, don't forget to go over like stuff from previous midterms as well, because they are like just go over the practice exams from the previous midterms, like the exams from the three exams. That should be enough, but that should be enough practice for the old stuff. And yeah, but yeah, again, tomorrow, we can go over more of that if you like. Anything that you still feel like uncertain of. I can still stay here if someone else wants to discuss something different, but yeah, if not, just think about what else you're having problems with, and we can talk about that tomorrow if that sounds good. Okay, good, good, good. You too, you too.
Oh, everybody's on. Okay. Can we quickly discuss
Mhm.
like the geometry for optimization?
The geometry optimization problem, do you have any one specific or
Can we do, let's say, there was one on a quiz. It was a semicircle question.
one on a quiz? Let me check.
It was a rectangle instead of semicircle.
Oh, yeah. I think yeah, it must be one of the most recent quizzes. Let me find it. Perfect. Good, good, good. That's we can go over that one. Yeah. Okay.
Yes, with Rocket Mortgage.
Let's see. Yeah. Oh, here it is. I have it written. Okay. So you want to construct a rectangle. Okay. So this was quiz 8. So we have to construct a rectangle. Okay, you have a semicircle radius 4. So the radius is 4, so there's 4 on each side. And you want to make a rectangle with the base on the diameter of the circle. So this is kind of like the diameter of the circle, right? So the base of the rectangle is going to be there, which is what you see in the picture, right? And the other two vertices of the rectangle are in the semicircle, which is what's happening here. So what the problem is asking is, oh, sorry, yeah. So 4 is the radius. So I should maybe write it like this. So here's 4 and here's 4. So the problem is asking like basically what are the dimensions with maximum area, right? Is the picture making sense?
Yeah.
Okay. So so what are the dimensions with maximum area? So like the idea here, like for example, you could call this half side of the rectangle x and this half side x, and the height y, right? So the area of this rectangle is based on height, which is 2x times y. Is that okay? Now the thing is like in all the optimization problems, you kind of need an extra equation to find a relation between the variables. So what's the relation that you could use? Well, here's like secretly a right triangle, right?
Yes.
If you see it here. So by Pythagoras theorem, x squared plus y squared, right, is the hypotenuse squared. But what's the hypotenuse? Well, the hypotenuse is literally the radius. Yes, so it's 4 squared, you see. So you can put here 4 squared. So you get like, well, here is more up to you which one you want to solve for, but it's more common to solve for y. So you can say that y equals 6 root of 60 minus x squared. So that makes a function like the area that makes it a function of one variable, right? So far so good.
Yeah.
And once you get to this function, is finding the critical point of that function. So what's the derivative of this function? you can use a product rule. So the derivative of the first factor is 2 times the second factor plus nothing you do to the second factor, and the derivative of the square root is 2 root of 16 minus x squared times by the chain rule minus 2x. Is that okay?
Yeah.
And then you set that equal to 0, right? That must be set equal to 0. So we want 0 to be all of this. Oh, you can cancel out the 2's. So you get something like this. There's a 2 that survives there. Okay, so there's a bunch of 2's, right? So, oops, like, yeah. Sorry, no, in fact, that 2 also goes away because, okay, now there's a bunch of them. So yeah, there's a 2 that goes with this 2, or with that 2 actually. And then there's these 2 and these 2 go away when because you're setting it equal to 0. So you just get minus x squared over, root of 16 minus x squared. Right, and then there are a couple of ways to solve this. Like you could multiply by the square root of 60 minus x squared on both sides. Right.
Yeah. Wait, why isn't it negative 2x squared?
Oh, it's just that. The thing is like, okay, these 2 cancel out, right? And then there was a 2. There was a 2 here and a 2 here, right?
Yeah.
So kind of, I divided the equation by 2 on both sides. If you prefer, you can put like a 2 here and a 2 here, right?
Okay.
And then you just divide by 2. So when you divide by 2, these 2 go away, right? Is that making sense?
Yeah.
And then, okay, yeah, another way to do this, like if you like maybe move the thing with negative to the other side, maybe it will look better this way. Yeah. So the 2's canceled, and then you multiply both sides by the square root in the denominator, so you get 16 minus x squared. So you get 2x squared equals 16, so x squared equals 8, so x equals 2 root of 2, right? And once you know that value, then the value for y is determined by the value for x, because y is 16 minus x squared root of that. So you get root of 8 as well. So you get 2 root of 2. Is that making sense?
Yeah.
So yeah, those were the dimensions of the rectangle.
Okay. Thank you.
No, sure, no problem. See you tomorrow then.
See you tomorrow. Have a good day.
You too.